This is video 6 in the playlist Reservations in Two-Way Slabs by Means of Yield Lines. We will handle case 6, which is a slab where on one side the end is fixed and the other three sides is simply supported. And those type of slabs we will handle 5 different types of reservations in the slab. On this plan view, schematically, you will see one continuous slab, concrete, which is simply supported on the edges, which is in orange, and its fixed support with beams, for instance, or walls, which is the dark green. So the dark green means the slab is continuous and it's clamped at that location. Case 6 is a reservation type, like it is described here. Case 7 is the corner square hole. Case 8, the edge square hole. And case 9 and 10, it's the centric hole, or it's a centric hole which is extracting yield lines. So this video is about case 6, where the slab is fixed on top and on the 3 other sides it's simply supported. Now let's consider the slab without any reservation in it, and we will calculate the maximum bending moment in the slab due to a uniform distributed load. We look at the yield lines. This is a corner where the one end is fixed and the other simply supported. So we use the 60-30 degree rule. Of course, this is only an approximation, but it fits it quite well. Maybe later on we will make a more detailed calculation to calculate this angle. So, but for the moment we will take the 30, 60, and 45 degree rule. That's also 60 and 30 degree, and where the two sides are simply supported, it's a 45 degree angle. Then we connect the yield lines, and because we have a fixed end, there's also a yield line according to that fixed end. Then we will have some geometry, S1, and S1 can be calculated by using the cotangles rule of a triangle, which means that the largest side of the triangle is equal to the height of the triangle multiplied by the cotangles of the two angles. Because this is 45 degrees, S1 is equal to S2. And because of the 45 degrees here, S3 is equal to S2. And then we can calculate S4 by means of the same type of formula. So we see that S1 is equal to S2 is equal to S3. Now let's try to calculate the maximum bending moment. We've seen the different yield lines, but those yield lines M, they are at the bottom of the slab, and M accent is the yield line on top of the slab. Is the fixed end bending moment. Usually, or when the top reinforcement is equal to the bottom reinforcement, then M is equal to M accent. You can always use another approximation for M accent, but this is the most common way of working. The work done by the external forces are then given by a summation of triangles and rectangular portions of the slab, And first of all, we consider 3 triangles on this side and the 3 triangles on the other side. And then we'll see 1, 2, 3. So we see that S1 times A, which is this total surface, plus S3 times A, this surface, times Q, the uniform distributed load, times the deflection divided by 3, because that's the mean deflection for a triangle. What's left is a rectangle with side A, and the other side is B minus S1 and minus S3. And this is times Q delta divided over 2, because delta over 2 is the mean deflection of a rectangular slab. We know that S1 is equal to S3 is equal to A divided by 1 plus square root of 3. And substituting this variable, we will end up with this formula for the work done by the external forces. Now, the work done by the internal forces are those bending moments projected to the rotation axis. And then we got M times B times the angle of rotation, which is delta over S2. So this is this case. We also have this bending moment rotating around this axis. So then we have M times B times delta divided by this largest distance, which is S4. This is this. And then on we also have the M accent, but M accent is equal to M. So this yield line rotating around this axis, and then that's why there is a 2 here. And it's also Bm times delta over S4. What is left is this bending moment projected to the vertical axis, which is A times M, and the angle is delta divided by S1, and the same for this side, so there is a 2. Substituting the variables gives you this formula for D. And for calculating M, then E must be equal to D, and we can then rewrite this formula. From now on, we'll call the maximum bending moment of a rectangular slab without a hole. We call this M0. Now let's check if this is okay. For a square slab, it leads to A is equal to B. So the M0 becomes this formula, and it's approximately QA squared over 30, which is indeed the maximum bending moment of a uniform of a slab uniformly loaded with a load where one side of the slab is fixed and the others are simply supported. Now let's look at an existing slab. The reinforcement which is in an existing slab without a reservation, we call it AS0. The bending moment, the maximum bending moment of the slab with a hole is M and is proportional to the load Q. And M0, which is the original design value of the slab without a hole, it's Q0 times C0. It means that the load of the original slab, of the bending moment of the original slab divided by the bending moment of the slab with the hole is equal to the load of the slab with a hole divided by the original load of the slab. So for the further calculations, we will use, instead of E, we use EX because we divide E by delta Q. It's just an easier way to work. And for D, we use dx, which is D divided by delta M. And when E equals D, then we will see that M is just equal to the uniform distributed load times EX over dx. So we'll use this formula. This means also that we will define bearing capacity as 100 times the uniform distributed load of a slab with a reservation divided by the original capacity of the slab. But instead of using Q and Q0, we will use M0 and M. So we will use in the slides BC, which is the bearing capacity. Now let's handle case 6. In case 6, we look at a slab. We draw the yield lines, like in a slab without a hole. We look at the geometry, and we look at the reservation, which is like it is indicated here on the slide, with dimensions D1, D2. Because there are many possibilities of the location of this reservation within the slab, that it is impossible to put everything in one formula. So that's why we have different cases of arrangements of holes or reservations. The reservation is marked by its length and width and by the position by D3 and D4. Because we are working with two-way slabs, it means that B, the largest side of the slab, must always be between A and 2 times A. If it's bigger than 2 times A, then the slab will only carry its loads in only one direction, and all the formulas that I'm giving now are then not valid. The horizontal position of this whole case 6, the horizontal position is such that the reservation will not cut the yield lines on the left-hand side, and they will not cut the yield lines also on the left-hand side from the other side of the hole. But it will be clear. In fact, it is simple. D2 plus D4, so this is D2 and this is D4. This distance from there to there must be between S1 and B minus S1. So it's, and of course, D4 must be smaller than S1. Otherwise, this will be outside those yield lines. D4 is also smaller than S1 divided by S4 times D3. And the vertical position of this reservation is that S4 is of course smaller than D1 plus D3, otherwise this reservation will fall outside of the slab. And D3 must be smaller than S4. That's to get this tip of the reservation within this yield line. Okay, now we'll give you a visual idea of what type of reservation this is, otherwise it's getting too complicated. This is a sketch of the slab. The dark line is clamped, and on the other side it's simply supported, and the orange one is where the hole is going to come. So this is a hole type 6. This also a hole type 6. You see this point and this point are inside the yield lines. The same happens here. This side is always inside the yield lines, and the right-hand side is never cutting the other yield lines. And the in vertical direction, it will always be on both sides of the horizontal yield lines. So this is also possible because there it's not cutting the yield lines, it's not cutting the yield line only in the middle on both sides of the yield line. So that's also case 6. And this is also case 6. So now you have an idea what case 6 hole means. It's just this type of reservation in a slab. So now we can go in a little bit more detail. The horizontal position, we fill in some numbers so that we know the formulas that we develop must comply with those conditions, or the formulas are only valid within those conditions. Type or a reservation like it is mentioned here, where the left and bottom, left bottom and left top corner of the reservation is outside the yield lines. This we handle. This is not case 6. So just be aware of that. Now let's look at it a little bit closer. We know what S1, S2, and S3 is, and S4 from the first slides. On this, again, the positions of S1, 2, 3, and 4 are indicated, and the values of D1, D2, D3, and D4. To develop the different formulas, we need some other parameters. This is x1. X1 is the distance from the yield line up until the support. So that's x1. So x1 is different from d4. Only when this tip of the reservation is falling or coincides with the yield line, then d4 is equal to x1. X2 is at the bottom, so it's where the edge of the reservation is touching the yield line. So that's x2. And y1 is the same, but in the vertical direction. We see then that x1 must be proportional to the angles of 30 and 60 degrees. So it means that x1 is equal to the 3 divided by square root of 3. This is d3. And x2 is equal to y1 because of the angle of 45 degrees, and x2 is then, if you look at the vertical direction, it's a minus d3 minus d1, and then you got here y2, which is y1, which is equal to x2. Now I must take care, because when we apply a load, the delta, the deflection, which is an unity, the delta is maximum here on the middle of the line, on this horizontal yield line. Looking at this side, for instance, at this portion, then when the center goes down with delta of a distance over a distance S1, for instance, then we know that in an intermediate distance x, the deflection is delta x. And delta x is then, of course, delta times x over s y. So this is valid for this portion. So you must always look at the mechanism that this part of the slab is rotating around this axis, and the same for the other axes. And then you will see that this part here is not rotating over delta, because that's where delta is, but over a portion delta x divided by s1. So we look at the different parts now of the slab. Like for this slab, that point there has a deflection of this. This portion has a deflection like it's indicated here, and this portion here has a deflection indicated by this. So just bear that in mind. Now we divide the slab into rectangular zones and triangular zones. And first we start with the rectangular zones, which are the orange parts of the slab. The mean deflection is a half, because remember we have divided by q delta. So that's normally it's delta over 2 of q delta over 2, but we divided by q delta. And then we look at the different rectangular portions. The first one is d1 times d4, and then times the deflection, which is d4 divided by s1, because this is not moving with the same amount as delta, but it's a fraction of delta. So we can go now to the other rectangular areas, which are, for instance, this is d3 times this length, and this length this length, it's d2 plus d4 minus x1 gives you that portion of the slab. Times, of course, again, d3 divided by s4. And so we can continue for this portion of the slab, and then for what is left, the bigger one, it's a, this is a times the total distance b minus d4 and d2 and s3. So we have this portion here, like that. Then we add up the areas of formed by the triangles, which is 1/3 of the deflection. The mean deflection is 1/3 of delta. And we will look at the corner, which is this one. It's A times S3, because it's 1, 2, 3, and there are 3 triangles. So it's A times S to 3 total surface divided by 3. Then we take the next one, which is x1 times d3. The surface is divided by 2 times the value of the deflection there, which is d3 over d4, x1 over s1, sorry, because this is the maximum deflection, and there it's a portion of the deflection. That's the portion. Then we do the same with the other triangles. And when we got this, you can regroup the different terms, and you see that the work done by the external forces are equal to this formula. Of course, when we are going to substitute all the different variables, it's quite ridiculous to write down the formula. So we'll keep it in this form to make it a little bit more playable. The work done by the internal forces, dx, is then equal to d divided by m delta. And the first contribution is the yield line where the slab is fixed. Projection to this rotation axis, of course, is b times the angle of rotation is delta over s4. So the delta is here, and there's the s4. So b over s4, taking into account this yield line here. The next one is this portion of the yield line projected to this axis, where the reservation is, the yield line is cut. So we got a total distance from there to there, which is b minus d4 minus d2 divided by the rotation angle, which is over s4. Then we take the next one, which is x1 divided by s4. So this is the projection of this yield line vertically to this rotation axis, and the angle is then s4. It's not a portion of x4 like we've done with the calculation of E, because now we are taking into account the angle of rotation. So when this piece of slab portion is rotating here with an angle delta, this is the same for every part of the slab. So that's why I divided by it as 4, which is the distance from there to there. Then the next is this yield line projected to this axis. So it's divided by S2. It's B minus D4 minus D2. Then we've got X2, this amount divided by S2, which is the angle of rotation. So it's this portion of the yield line projected to this rotation axis, and it gives you this amount. And then we can go on for the other portions, like for instance, this yield line here projected to the rotation axis A is of course A divided by S3. And then we can regroup a little bit or fill in some parameters, and we got these are the formula of dx. We know from the previous slides that m is equal to q times ex divided by dx. And when doing so, we must take care of those different conditions. You have a horizontal position of the reservation and a vertical position of the reservation. Let's just make an example. Rectangular slab 9 by 6 meter, clamped on the north side and simply supported on the other 3 sides. The depth of the slabs is 250 millimeter, the concrete cover 40 millimeter, and the floor finish is 1 kilonewton per square meter, and a mobile load of 5 kilonewton per square meter. And the question is, what is the needed reinforcement? With, of course, a reservation in the slab as indicated here, with the situation with the position 1.2 and 2.5 meters, and it's a reservation of 2 by 4 meters. So it's quite a reservation that will be made in the slab, and we want to know what is the needed reinforcement in this slab, taking into account this reservation. The load in ULS, ultimate limit state, is then the proper weight of the slab, which is 0.25 times 25, plus the floor finish, and this times 1.35, plus 1.5 times the mobile load, gives you 17.29 kilonewton per square meter. The different parameters, and then the conditions that you must apply to. So I've rewritten that just to make sure that we are all right there. For instance, for this restriction, if you put in the numbers, you will see, okay, this is fine, this is okay. The other condition, D for smaller than 0.36a, we put in the numbers, okay, this is okay. The same for this condition, and we continue until we got all the conditions. All the conditions are fulfilled, so I can use case 6 in this particular rectangular reservation in the slab. This we've known from geometry. We can calculate it now. It's 2.2 meters. The value of x1, the value of x2, and then we can put in all the different numbers. So we are now calculating the maximum bending moment, of course, still assuming that the reinforcement on the top will be equal as the one on the bottom. We calculate EX, we find 16.144. We calculate DX, which is 10.711. And then the maximum bending moment is then equal to 26.1 kilonewton meter per meter. We look at the lever arm in the X direction, which is the total height of the slab minus the concrete cover minus the point of gravity of the reinforcement in X direction, and it gives you 200 millimeter. I've chosen as diameter 10. If we will, when we have a result which is not indicating that where diameter 10 is not fulfilling the conditions, then we have to redo the calculations with another diameter. So this is just a chosen diameter. For slabs, most of the time 10 will be enough, 10 or 12 millimeter. The lever arm in the Y direction is the second layer of reinforcement in the other direction, is equal then to 205 millimeters. And we are calculating the mean lever arm, and this mean lever arm of the reinforcement is then 202.5 millimeters. When we are not using the mean lever arm, then we have a bending moment in the X direction, which is different from the one in the Y direction, and we can still calculate the slab, but then we have to adapt our formulas. The needed reinforcement in X and Y direction is then the bending moment divided by the lever arm, but we add 10% because this is an upper bound method. We put in the different numbers, and we need 362 square millimeters per meter in X and Y direction. So a diameter 10, 5 diameters 10 per meter will be okay, because then you got 393 instead of 362. So the reinforcement is for top and bottom of the slab. It's in the X direction and the Y direction. We will now look at another example. We have an existing slab which is reinforced in two directions, and that the only thing we know is that the top reinforcement is equal to the bottom reinforcement, and we are going to make a reservation in this slab, in this existing slab, with this size. We do not know how much reinforcement is there in the slab. We can only suppose that the slab was calculated in a proper way. So how will we deal with this problem? We know what the maximum bending moment without the hole. We know this is M0. We divide by Q because the load we don't know where it is designed for, but M0 over Q is equal to this formula from the previous slides, and we got 1.582. The maximum bending moment with the hole is then M over Q is EX over DX. It's only depending on the geometry. We can calculate EX and DX, and we find 1.507. So this means that the bearing capacity is 105. So by making the hole, you increase the bearing capacity. I mean by that, when this is designed for a bearing capacity of Q, uniformly distributed, you make a hole in it, and there is no load anymore where the hole is, then you can put on the other areas 5% more load, because this load disappears. So the answer to this problem is then, yes, you can make the hole in the slab. Now we can wonder, just to give you an idea how you can play around with the different formulas. For instance, you can have an existing slab, and there must be made quite a large reservation in the slab, and we have the choice of where to put this. Now we can put this reservation in the top left corner, or we can put it a little bit up or more up, like here. So what will now be the best situation? We know that alpha 4, which in fact it's D4 divided by A, D4 divided by A is alpha 4. So D4 is between 1 and 1.1 meter. And we wonder what is the best position. So these are the two extremes. This is D4. D4 is 0 in this case, and D4 here. D1 was 3 meter, A was 6 meter, B was 9, D2 was 4.5, and D3 is A minus D1 minus D4. And this corner here, this distance is D3, sorry, and this is D4. So we can calculate D3, it's 3 minus 6 alpha 4, because the unknown is D4. So D4 divided by A is alpha 4. Yeah, like this. Because we have now a parameter and where we want to optimize through this parameter D4. And this parameter must be between 0 and 1.83, which is the difference between this is 0 and this D4 is 1.83 times A. These are the different parameters. We can now calculate S1 and S4. This is the horizontal position. We know that in the horizontal position, we must obey this rule, otherwise it's not good. And we can put in the different numbers, and we see alpha 4 must be between 0 and 0.384. Okay. D4 smaller than S1. We put in the numbers. And then we got alpha 4 smaller than 0.366. So this is governing. Then D4 must be smaller than this. We can put in the different numbers, and we can rewrite it as alpha 4 must be smaller than 0.183. In the vertical position, S4 must be smaller than D1 plus D3. We can put in some numbers, rearranged, and we find the same as what we got there. And then D3 must be smaller than S4. We fill in the numbers, and alpha 4 must be bigger than 1.34, than 0.134. So out of all those conditions, we know now that alpha must be smaller than 0.183. Then we can rewrite the formula of the bearing capacity by assuming that, of not assuming, by making that D4 is equal to alpha 4 times A. And then you can rewrite the formula in this way. We can put it into a graph. On the x-axis, it's alpha 4 is between 0 and 0.183 because that's the maximum limit. And the bearing capacity goes then from 100 to 130. It is the red line, and you will see that the bearing capacity increases when the hole moves towards the center. So the worst position is the reservation in the bottom left corner when the D4 is 0. And it is when it is less severe when the reservation is put fair the middle. The blue dotted line is just a straight line from the horizontal, so that you can see it's almost linear except on the end, at the end. Now we look at the different cases, and the bearing capacity when D4 is 0, it's 101. And when it is 0.92, which is in between, is 114. And when it is in the middle, it's 120. So this is corresponding with this value here, and with 0.092 with this value. So you see that this is the best position, or let's say that all those positions are okay for the slab. And when you have the when you choose this, then you increase the capacity of the area which is left over. Now let's take another example just to show you how you can play around with different formulas. We will now have a slab. On one side it's fixed, on the other side simply supported, and we need a reservation in the slab for instance an electric panel, to put an electric panel on it, so where the cables can come through the slab. And now we will see in a slab of this type, in a reservation of this type, going from there to there and there, what is now the best position, or what is the influence on the bearing capacity of this type of reservation. So it starts here with D4 is 0, and then it starts with D2. It's the width of the reservation. It must the smallest value is here, and it's 0.367A, and this is 1.134A. Now we take the two limits and the different values of the parameters. D4 is 0 because it's just on the edge. And our parameter now is D2. This is the variable parameter, D2. And we know from the geometry, D2 can go from 2.2 meters to 6.8 meters. And this is D2 over A. So those were the conditions. We can calculate S1 and S4. The horizontal position, we will check all the different conditions. We check again the horizontal position, put in some numbers, and we simplify it, and we see that alpha 2 must be between those two limits. D4 must be smaller than S1. Again, this is okay. D4 smaller than that. We calculate it, and this is also okay. The vertical position, S4 must be smaller than D1 plus D3. We put in the numbers, and we see, okay, this is fine. And D3 smaller than S4. Put in the numbers, this is also fine. So we fulfill the conditions for case 6. We can now fill in all the known parameters in the formula for the bearing capacity. And we see that this is a function of the parameter D2, which is the width of the longest side of the reservation. And this is, of course, more or less a straight line. For alpha 2.367, then for alpha 2, which is D2, equals to 1.134 times A, we got 86 as bearing capacity, and in between 93 and the smallest hole we will have 99. So this hole is more or less not touching the bearing capacity of the slab, and this is preferable the right place to put in the reservation. All other reservations are lowering the bearing capacity of the slab, so which can create a problem. Especially this one, this will lower the bearing capacity by 14%.